One project that we're really excited about and in the beginning phase of development is to develop this fiber-based miniaturized microscope. So one thing we could do is to use it like endoscopy, but that gives you a microscopy resolution. So you can imagine we can use this for small animal experiments so that you don't have to euthanize animal every time you do an experiment. You can basically just insert this tiny microscope into the GI tract of the animal and monitor it longitudinally, see how the infectioning is happening, how the therapy is working. So this way, you can do this drug development in a much more realistic scenario. And then in the case of human patients, we already have endoscopy in clinical practice, confocal endoscopy that you can really just image cells. But what is lacking right now is that the size is still on the millimeter scale. So if you want to reach into smaller ducts in the lung or even in small kids with smaller ducts, so we need to bring the size an order of magnitude down. So that's where our proposed technology that could work and make a difference in the clinical applications. So for example, if we're studying GI infection, we can inject fluorescently labeled bacteria into the animals, right? So without this technology, what we have to do is, let's say we use treatment 1 and we want to monitor the progress. What we're going to do is we're going to euthanize the animal at this time point and then euthanize another animal at the second time point. And we're going to do a bunch of animal experiments to see if this therapy is working, considering the errors between per animal heterogeneity. With this new technology, what we can do is we can just use this microscope and insert it deep into the GI tract. And we can see how the bacteria is reacting to the therapy in real time. So first, we get to see dynamics, which was not possible before. And second, we can monitor the same bacteria infection in the same animal using the consistent therapy longitudinally, which was also not possible before. So that is the hope, that is the long game, that is our ambition. The thing with imaging technology is that you always have this trade-off between depth and the resolution. So for example, if you do MRI, you can penetrate through the entire body, but your resolution is like a millimeter, centimeter. But for optical microscopy, we can look at sub-micron resolution. That means we can look at subcellular features. But at the sacrifice, at the cost of both depths. So if you just do microscopy, you can penetrate at best 1 millimeter. So that's why most optical microscopy has been done on dead sectioned tissue. The second thing is the field of view. So MRI, you can do a full body scan, no problem. Ultrasound, you can do an entire uterus scan, no problem. But for optical microscopy, if we can get like a millimeter, 1 millimeter by 1 millimeter field of view, that's already awesome. The technology we are designing in the microscopy, we are targeting a field of view of 50 microns to 100 microns. So the things we target is mostly subcellular features. We probably still need multimodal approaches to give us the entire picture. So that is the niche of this technology.